We've been discussing how to describe a variable with numerical methods. And so far we've talked about where's the center of your data, right? And we've focused mainly on the median and the mean. But beyond that, there's more to a variable than just where the middle of it is, right? And so what we want to turn to next is how spread out is your data. And to highlight this, I want to look at just so here I have kind of so each of these sets of data have 5 values in them, and I've tried to put them on a number line, and I tried to be somewhat accurate. Yeah, so we can see in the blue here we have 2, 6, 7, 8, and 12, and the others follow from there. And if you wanted to work through it, so number 1, all of these are symmetrical. But number 2 is all 3 of these have a mean of 7, right? So if we add up the blue, that's what, 8 plus 15 is 23, plus 12 is 35, divided by 5 is 7. So all of these have a mean. The mean is equal to 7. And so, and in fact, the median is as well. Median is equal to 7, and again, remember when we have symmetrical data, that's gonna happen. But clearly these are not the same 3 sets of data. In fact, if we want to think about how spread out this data is, we have different. Yeah, we're gonna have different amounts of spread here, and so. So one thing that we might talk about is the range, right? And we've covered that here in this chapter as well. But notice that the blue and the yellow both share the same range, right? They range from 2 to 12, or they have a range of 10. And so range itself does not fully tell the story of how spread out, or how spread out, what's the dispersion of your data. And so here's where we turn to the idea of variance and standard deviation, and we'll talk about how variance and standard deviation are basically 2 sides of the same coin, in that standard deviation is simply the square root of the variance. So both of these are tackling the same issue. And to sum up, what they're essentially going to do is they're going to look at how far each of the data points falls from the mean. Right, and we talked about with regards to mean, we made a point that the difference, or the deviations from the mean, we already looked at that when we looked at mean, right? And so each data point is going to not necessarily be right on the mean. Now, obviously, some may fall on the mean, and in fact, in this case, we will see them fall on the mean, at least for the number 7. So for instance, with this blue line here, we have values 2, 6, 7, 8, and 12. And we already saw back in our discussion of mean where we compared it to the deviation. Supposed to be an I in there. Deviation being 2 minus 7, right? And so we have a -5 deviation. And this would be -1. We have a deviation of 0, right? So the 7 falls right on the mean. We have a 1, and we have a 5. And as we talked about discussing mean, if we were to just simply sum these up, we would end up with a sum of 0. And so how we're going to talk about, and the important part here is that would be true for all of these, right? The red and the yellow. All of them have a sum deviation of 0 from the mean. And so we can't just look at how far or what's the total deviations within the data set, right? So all of these would have 0, and we'd have no way to say, this, say the red is less spread out than the yellow. We wouldn't be able to compare if we just said we're going to add up the deviations. So instead what we're going to do is we're going to add up the squared deviations. Okay, and in fact, that's what becomes our measure of variance. Or variance is simply the sum of the squared deviations. Or it's the mean. So we add them up and then we divide by the total number. Okay, so let's walk through. Let's 2, 6, 7, 8, 12. 2, 6, 7, 8, 12. So 2, 6, 7, 8, 12. And remember, so the mean is 7. And so our measure of variance, our way of saying one variable is more spread out or less spread out than another, is going to be what we call the variance. And this is going to change slightly depending on whether or not we are dealing with a population or sample. So in this case, we're going to walk through it as though this is the population variance. Okay, and we use so this is sigma, and so sigma squared is going to be the sum. Remember the also sigma, but the uppercase is we're going to use x minus mu. Okay, so here's where it's important to remember what mu means. We already see it popping up, and then divided by n. So a lot going on there, but remember what I said we're going to use. We're going to use the deviation. So this x minus mu is the deviation, right? So let me just set this off aside. So x, I did not leave myself very good space here. See if I can slide this down. Okay, so x minus mu is the deviation from the mean. So as we already calculated, right, this is going to be -5, -1, 0, 1, and 5. And we said, as is true for all deviation sums, that this would sum to 0. Even if it's not symmetrical data, it would still sum to 0. So we're not going to sum this up. What we're going to sum up, remember, so this summation here, let me just switch colors here. This summation works over this whole area here. So all this is included within the summation. And so we need to go ahead and square this. We're going to do x minus mu squared, which is just the square of this column. So -5 becomes 25, -1 becomes 1, this becomes 0, 1 becomes 1, and 5 becomes 25. Okay, next we're going to sum these. So this becomes, what is this, 52. Okay, and then 52, so 52 is the top, so sigma squared is 52 divided by n, which is 5. And so our variance here is 10.4. Okay, so we now know what the variance is. Now the variance by itself is not very instructive unless we have another variable to compare it to, right? So the whole point of a measure of spread here is so that we can compare one set of a variable to another set or a different variable, right? And so in this case, we do have, we can compare it to, let's walk through the red case. So 4, 6, 7, 8, 10. So 4, 6, 7, 8, 10. And a good process might be for you to pause the video here, see if you can walk through the process yourself. And again, we're trying to compute variance being sum x minus mu squared divided by n. So feel free to pause it and see if you can come up with the solution. Yeah, So let's double check and see how you did. So x minus mu, again, the first step is to calculate that deviation. And again, the mean is 7 here. And variance is going to work even if the means aren't the same. So even if our data sets or our variables had different means, we could still compare the spread between them. So this is going to be -3, -1, 0, 1, and 3. Right, and then the next step, we need to square it. This is going to become 9, 1, 0, 1, 9. We're going to sum those up. We get 18, what is that, 20. So the variance is 20 divided by 5, or 4. Okay, and so now we have, so just to remind you, the variance of the blue, I think, was 10.4. And so we have a variance measure for both of these. And so what we can then say is the red variable is less spread out. It's more clustered around the mean. And we could do that one last time with the yellow, and perhaps you can even guess where that's going to fall based on the other values. But we'll 2, 5, 7, 9, 12. 2, 5, 7, 9, 12. And again, x minus mu, where mu is still equal to 7. So this is going to be -5, -2, 0, 2, and 5. X minus mu, again, feel free to pause this if you want to work through it yourself. That's 25, 4, 0, 4, and 25. And so this time when we add it up, remember again, variance being the sum of x minus mu, all of that squared, summing up all of that and then dividing by n. Again, we're in the population variance here. This gives us 58, and so we have sigma squared equal to 58 divided by 4, which, divided by 5, which is going to be, what, 11.6. So at the end of the day, we have 11.6. We had blue at 10.4, and we have, I don't remember what color I made it as. Red, was it red? It's going to annoy me. Okay, red was 4. Okay, and so we now have a way to order the spread of these three variables. Now, of course, in this simplified case, we probably could have picked up on that or made that assumption without this calculation. We could have just looked at those 5 numbers. But it's not always going to be as clean as that, and so this method gives us a kind of uniform way to always be able to calculate the variance and compare across different variables. The standard deviation, to introduce that, is simply we just take the square root of these results. And we refer to that as just sigma. So sigma squared is the variance, and sigma is the standard deviation. And there are reasons to use standard deviation compared to variance, and we'll work through some examples to show why that might be. But just to introduce it, sigma is just the square root of 11.6, which I don't know off the top of my head. Same thing here, sigma is square root of 10.4, and sigma is 2, right? Let me just highlight that these are going to maintain the same order, right? So the square root of so sigma in this case is going to be 3.22. Sorry, I've jumped up here to the only open space I have, and then I'm just looking these up quick. The square root of 11.6 is 3.4. Okay, so whether or not we take the square root of it isn't going to change the order. So it's still the fact that yellow is the most spread out, red is the least spread out. Yeah, and we'll talk more about why specifically standard deviation. The other thing to note is, again, these are population variances and standard deviations. When we turn to samples, it's almost the same process. There's just a little tweak in there as far as what we're dividing by. So if you get your head wrapped around this, then you'll have variance. You'll have the sample versions figured out as well, with just remembering the exact formula. So we'll be back with some more videos discussing this.